Welcome to Analytic Methods for Lawyers. This lecture is on statistics and statistical testing, as well as the concept of statistical power. And a lot of the traditional study in this area involves how likely a particular statistic or a set of statistics we see would take on the value they do if some circumstances were true. But this method works well only if the statistic is powerful. Statistics that don't vary much depending on the output of some process really aren't very powerful. And so what we want to do here is to probe the importance of statistical power. In other videos, we'll learn about problems that can occur when the statistic is adequately powered, but it's still not used properly. And I want to start with kind of a fun example and teach you about leopards and jaguars. So let's look at this picture here. And kernel's loading up, and there it is. So what would you say that animal is? My opinion, it could be a leopard, could be a jaguar, maybe it's a cheetah. But anyway, let's ask a neural network to take a look at this photo and see what it thinks it is. So we're going to use the Wolfram Language image identifier. I'm going to give it a hint that this is some kind of big cat, and we'll see what it decides. So it's thinking a little bit, and it has decided 68% chance it's a jaguar, 29% chance it's a leopard, and then maybe a cheetah, a snow leopard, and it's certain that it is a big cat. All right, so we've gotten some confidence, but if we wanted to rule out the possibility that this was a leopard, we've still got a 29% possibility that it is a leopard, and so whatever testing our image identifier is doing isn't really powerful enough to rule out the possibility that this could be a leopard. But let's suppose we now have a different image to look at. We have maybe some image processing has been done on it. And you can see visually, I think, even on video, that this is a clearer picture. Let's see now what our computer, our neural network, thinks that it is. And if we run it, now we're 84% sure that it's a jaguar, 16% sure that it's a leopard. We've pretty much ruled out cheetah. We've ruled out snow lion, and we're still 100% certain that it's some kind of big cat. So we're a lot more confident that it's not a leopard. And yet, the animal, it's the same animal. I promise you it is the same animal. What's changed is that in effect, the data is better and the methodology is improved to look at it. So in some sense, we're able to have a more powerful test to examine the data. And so this is kind of analogous to what we do in statistics, is we want to come up with ways of looking at numbers, not necessarily jaguars and leopards, but looking at numbers in a way that we're really able to make distinctions between one set of numbers and the other. So with that analogy, let's talk about statistics themselves. So what is a statistic, really? A statistic can be anything. It's just any value, could even be a set of values that's derived from other values. So a statistic, a conventional statistic, is the mean of some data. You add it up and divide it by the number of numbers. The median, how many numbers, you find the number for which half are below and half are above, the maximum number in some set. And so it's basically a formula based on data. And in fact, you can think of a statistic as a little computer program that yields some output. And so one thing we're often interested in doing is determining whether the data we see could have been produced by a certain distribution or a certain factory, and we're going to use a statistic on that data as our probe. So here I've generated a bunch of data points. I believe there are 100 of them. What we're curious about is whether that sample of data could have come from random draws from the normal distribution with first parameter 0, second parameter 1, which I've told you in previous videos we just call the normal distribution. So let's do an experiment. Okay? What I'm going to do is I'm going to take data that I know is drawn from that normal distribution. I'm going to use our random variate command, which I've told you commands the factory to go into action. I'm going to make this factory very busy. I'm going to ask it to do this experiment 1,000 times, and I'm going to tell it each time you do the experiment, I want you to produce 100 numbers. I've seeded the random number generator. I discussed the purpose of seed random in an earlier video, and we're going to keep the output to just 8 lines so we don't have whatever this is, 100,000 numbers visually cluttering up our notebook. I'm going to assign the output to RV100. So I hope you've done the introductory lectures, and so you have a better idea what this code is about. But really what we're doing is we're producing 1,000 samples of 100 numbers. All right, so we run it, and in just a moment, it is going to be done. Good. Okay, so now what we want to do is we want to compute a statistic on that data. And what we're going to do is we're going to take each set of 100 and we're going to find the maximum of it. So we're going to map the maximum function over this big array of numbers. Again, we're going to truncate the output so we only see 8 lines of it, and I'm going to assign that value to max 100. Okay? So there we are. We have 1,000 different maximums that came from our draw of 1,000 different examples of 100 numbers. Okay, so I've shown you one statistic on that data, but really I just want to be clear, there are a zillion statistics I could compute from this data. I could take the mean of each row, and then take this distance between each element and that mean. I could square each of those elements, and I could add up the squares. And then I could divide that by the number of data elements minus 1. And while that might seem an awfully complicated, arbitrary thing to do, that program has a name. It's called the variance. And so I could compute the variance and make a histogram of it, actually. That's what it looks like. Or I could compute something really weird. I won't even go through what this program does, but it's just, if you look at it, the only thing it's doing is it's taking the data, and I'm going to compute something I call skew. I could compute the skew and make a histogram of that. And so there are just tons of statistics I could generate out of the same data. But let's go back to my original proposition and look at the sampling distribution of the max statistic. And this is not the same thing as the underlying distribution. The underlying distribution was all the numbers that we got. But now what I'm doing is I'm saying, let me take each row of 100 numbers and let me find the maximum of each of those rows, and let's look at the distribution of the maximum. Okay? So we can make a picture of that. Let's take a look. All right, there we go. Let's be crystal clear what we're looking at here. This is a sampling distribution of the max statistic. That is, we've taken our underlying distribution, which was normal 0, 1. We've run it 1,000 times. With each time we're drawing 100 picks, and we're looking at the maximum. That's not the same as the original data that we have, which came from who knows where. Okay? So, what we, and you'll notice, by the way, that this clearly is not drawn from normal 0, 1 in the sense that its peak is at 2.5. For a normal distribution, you'd expect to see the peak at 0. And that's because we're not looking at the underlying distribution here. We're looking at what were the maximums each time we picked 100 samples from the normal distribution. So I hope I've made that clear, that this is a sampling distribution. What we'd now like to see is what's the maximum of our sample, because if the maximum of our sample was like 26, then we could say, look, when you're drawing 100 numbers from N01, the maximum is never as big as 26. We never experience that. And that leads us to conclude that our data must not have been drawn from N01. But what if, when we compute the maximum of our data, it turns out to be 3.4? Well, it's unusual, but it's not completely impossible that you would get 3.4 as the maximum if you were drawing from N01. And of course, if we got something like 2.2, we would be able to say, look, there's no way we could say this isn't drawn from N01. Doesn't prove that it is, but we certainly don't have any evidence to disprove that hypothesis. So let's take a look here at our own data. If we compute the maximum of our sample, it's 2.7, which is high, but it looks like there are a lot of instances in which N01 produced something as big as 2.7. In fact, let's run a little code to see how often that's the case. And it turns out that in 297 times out of 1,000, even if you were drawing from N01, you would get a number as big as 2.71224. So you haven't really disproven a hypothesis that our data, those 100 numbers we picked at the beginning, came from N01. You haven't proven that they were, but you haven't disproven that and shown that they couldn't have been. So maybe, though, the reason that we're not able to disprove that null hypothesis that our data is coming from N01 is because we're using a lousy statistic. Maybe it's like we were looking at the jaguar through a blurry lens and therefore saying, I don't know, it might be jaguar, might be leopard, who knows. Maybe there are other statistics other than the max that are more powerful at picking up things that aren't drawn from N01 or otherwise. So let's try another statistic. Let's try the median. Okay, so I'm going to map the median over our 1,000 samples of 100 each. There's our distribution, and what's our median? Our median is 0.119, so maybe about here. Let's see on how many occasions, if we were drawing from N01, we would expect to see a number as big as 0.119427, and it's only 17.2% of the time. Now, is this strange? Because when we use the max, we were saying, well, it could happen 30% of the time. And when we're using the median, we're saying it could only happen 17% of the time. What's going on? And what's going on is precisely the jaguar and the leopard. I'm using the median as a more powerful statistic. It's better able to discern when your data isn't being drawn from, for example, the normal distribution. So, what this is establishing is that your choice of statistic matters and that you may not be able to detect a departure from the null hypothesis if your statistic isn't powerful enough. Okay? Now, maybe there's something better than the median. Maybe the mean, or maybe the cube root of the third biggest number is the best statistic. It's actually somewhat difficult to figure out what is the most powerful statistic. There are something called the Neiman-Pearson lemma, which helps us figure it out. That's sort of beyond the scope of this course. But what I want you to understand here is that the probability of a type 2 error, which we will or have covered in this course depending on the order in which the material is presented, a type 2 error is a failure to detect something that is in fact the case. So it's a false negative. That the probability of a false negative, you're saying, I don't know if it's true or not, depends on the test that one uses. And therefore, when someone says they were unable to disprove the null hypothesis, it could be because the null hypothesis can't be disproven, even by the most powerful statistic, or it could be that they're using a lesser powered statistic, and therefore have handicapped themselves in the quest for truth. Is the reason that we're not confident that that animal is a jaguar is because, well, it really could be a leopard, or because we're using a poor telescope, a poor camera, to try and figure out what it is. Let's now do a second experiment to help us further understand this notion of statistical power. So let's seed our random number generator, and let's draw 20 numbers from a normal distribution. And we're going to do it 1,000 times. And then what we're going to do is to figure out the mean of those 20 numbers. Okay? So we're going to draw 20 numbers. We're going to do the experiment 1,000 times. And then we're going to see what the mean is of those 20 numbers. So we should end up with 1,000 numbers, because each of the 20 numbers will have a mean. And we're going to call that T20, right? And so here are our 1,000 numbers. You can see that because I've used terse, it's elided the middle 972. Okay, now let's figure out at what value do 2.5% of the numbers of these means lie below it, and at what number do 97.5% of the numbers lie below it. So we're basically in between these two values. 95% of the numbers lie in between these two values. Okay, so what we've seen is that in our little sample, 95% of the numbers lie between negative 0.407 and positive 0.401, blah, blah, blah. Okay, so to do a little bit more work, I need to teach you a function. We're not going to use it all that often, but it's very handy here, which is interval member q. So interval member q is a Boolean function. Remember, Boolean functions end in q. They return true or false. And it just says, hey, give me an interval. Okay. And I'm going to give you a number, and you tell me if the number lies within the interval. And so hopefully, even before I run it, you're able to tell me, wait a second, 0.53 does not run inside that interval. It's outside, whereas 0.03 does. So let's just check. All right, so that's what interval member q does. If I give interval member q two numbers, it's going to return a list of trues and falses. And so hopefully you're going to realize, well, this number lies outside of our interval, so I'm going to get a false, and this number lies inside our interval, so I'm going to get a true. So hopefully when I evaluate this, I should get a list saying false, true. And indeed, I do. Okay, so now what do we want to do? Here's my question. Supposing, in fact, we're not drawing from N01, we're drawing from N01.1, a slightly different normal distribution with a slightly higher mean. How often would looking at the mean of those 20 numbers, how often would it be outside of the interval that we see in looking at N01? Remember, this is computing where 95% of the means will lie. But I'm just wondering, if we draw from N0.11, how often will the mean of 20 numbers drawn from that lie outside the mean that we get, or the interval that we get from N01, and so we'll be able to say, oh, I don't think that's drawn from N01. So let's do this experiment. Okay, we're going, and you're kind of seeing the results here. Let's kind of get rid of those results. All right, so what we're doing is we're getting 1,000 we're running an experiment where we take 20 draws from N0.11. We're doing it 1,000 times, and we're computing the mean. And then we're going to figure out how many times does that mean lie inside the interval we computed before, and how many times does it lie outside the interval we computed before. And what we find is that most of the time it lies inside the interval we computed before, and therefore even using the mean, which is a pretty powerful statistic, isn't good enough to detect draws from slightly different distributions. It just can't be done. But what if, instead of looking at draws of 20, we look at draws of 200? So let's do the experiment again, okay? Here I'm going to draw from N01. I'm going to do my experiment 1,000 times, but instead of drawing 20 draws each time, I'm going to draw 200. And I'm going to compute the 2.5% and 97.5% quantiles. We'll call that interval 200. You know what? I think that map knot is needlessly complicating. Let's get rid of it. Then what I'm going to do is I'm going to ask the same question, which is how often would the mean of 200 draws from a slightly different distribution fall outside of this interval that I computed up here. So let's run this code. And now we're saying that it's still 695 times out of 1,000 we're not going to be able to detect things, but 305 times we would. So we're on the right track. It's just that apparently for differences this subtle between N01 and N0.11, even 200 draws isn't enough. So we could do it 1,000 times. What the heck? That's easy enough. Let's do it 1,000 times. All right, we'll just change this name to 1,000. We'll change this 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 to 1,000. And we'll change this to 1,000. Okay. And now we're getting better. Now we're with 1,000. With 1,000 draws, now most of the time our mean is going to lie outside of the interval that it would have lain in had we been drawing from N01. And so it looks like with enough draws we can start to do better. And in fact, we can automate this process by writing a little function, power analysis, where we now have an arbitrary number of draws, okay, n. And so let's do this, and now let's make a list line plot and see how we do as the number of draws goes from 2 to the 4th to 2 to the 12th. Okay, so boom, ba-doom, 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 and we can see that when we start to get up, I don't know, maybe around 1,300 draws, we're able to discern as small a difference as draws from N01 as draws from N0.11. And so what we learn is that for detecting small differences, you may need a lot of draws. Even with the best statistic, even with the mean, you may need a lot of draws to avoid false negatives. Okay. Now, if we want to find, supposing the data doesn't come from something very, very close like N0.11, but it comes from something a little bit more different, N0.31. Or you could imagine it being an even more subtle difference, N0.031. We might want to look at the frequency, and I still think this map knot was a complicating mistake. We're just going to get rid of it here. We can take a look at how we do under those circumstances. So here we're going to run 3 different scenarios. One we're drawing from N0.11, one we're drawing from N0.31, one we're drawing from N0.031, and what we see is, this takes a moment to compute, it's doing a lot of chomping, is that when the difference is very, very small, Even getting 2,500 samples may not be enough to tell you that you're drawing from something different than N01, that you're going to have a hard time disproving the null hypothesis. If we're looking at a gross difference, we don't need that many samples. We need, looks like to me, maybe 200 samples or so. And again, if we are drawing from a difference where we're drawing from N0.11, we've seen before it looks like we might need 1,300 samples or so in order to conclude that we're not drawing from N01. Okay? So what we've seen is the test matters and the sample size matters in trying to determine whether your sample is drawn from something other than the null hypothesis, your original hypothesis. Let's actually put this learning into practice and do an experiment here. Supposing we've got a vaccine that we think it'll reduce the infection rate from a disease. And we're concerned, though, about how many people do we need to test this vaccine on before we can really say that it's working, because it's not costless to run the test. And we want to be pretty certain. Maybe we want to be 99% certain that whatever effect we find is not due to chance. And yes, there are ways we can work this out mathematically, but I kind of think it's useful to do just a simulation here and see how many people we're going to need. We're going to set up a null hypothesis, which is that the vaccination is useless, and that therefore we kind of expect the infection rate of people among unvaccinated and vaccinated peoples to be the same. So we're going to form a ratio of people who get the disease who are unvaccinated, we'll put that in the numerator, to people who get the disease who are vaccinated, we'll put that in the denominator. So a high ratio means the vaccine is working well. Disease is much more prevalent among the unvaccinated. Something below 1 would mean that the vaccine is somehow counterproductive. It actually causes people to get the disease, or at least it's associated with getting the disease. And a ratio around 1 would mean the vaccine's not doing much either way. We should assume, by the way, that our treatment and non-treatment groups are alike in all other ways that we know of. This is a fully blocked experiment. And we should also assume it's a double-blind experiment so that neither the subjects nor the medical workers know whether a given person got the vaccine or whether they got a placebo. So we're going to write a little function here that computes the disease ratio statistic in an experiment. And the function takes 2 arguments. It's going to take a first argument, which is the prevalence of the disease. So that's 20% if basically you do nothing. N is going to be the number of people in our experiment, and I'm going to insist that it be even because we're going to chop the group in half. Half are going to go in here in the unvaccinated group, and half are going to go down here in the vaccinated group, and we're going to form this ratio of how many people actually get the disease who are unvaccinated to how many people actually get the disease who are vaccinated. This little max here is just to prevent division by 0 in the unlikely event that it were to occur, right? So we're going to build on that. And by the way, let's just see this function in action. Disease ratio statistic. I'll say the prevalence rate is 20%. I'll do 100 people. And in this random setting, it came out to be exactly 1. It was the same. If I do it the second time, this time it came out to be 7/8. I'll do it a third time. This time it came out to be 12/7. And so you're seeing that when there's no real difference, the vaccine's kind of useless, we get numbers of ratios that are roughly 1, although not exactly 1. All right, so let's actually now create a function that runs this experiment iters number of times, where iters is an optional argument, and by default it's set to 10,000 times. That's going to get us 10,000 of these fractions. We can then turn that into a distribution and through empirical distribution, and then look at some various functions of that distribution. So there's our function, disease ratio distribution. We're now going to run it with a 20% infection rate, and we'll just run it 16 times. Maybe we only need 16 people in our experiment. Wouldn't that be nice? So here we go. Okay. And we're going to look at the survival function of the disease ratio distribution. On how many occasions will this ratio be greater than 4 as a matter of chance? Okay? And it turns out that even if the vaccine doesn't do anything, because the disease rate here is the same as the disease rate here, 15% of the time we're going to get, with just 16 people in our experiment, 15% of the time, even with a worthless vaccine, we're going to get that it reduced the rate of disease by a factor of 4. So I wonder how many people we really do need in our experiment before a factor of 4 we can say that that's suggesting that this vaccine is working. So here I'm going to let n, the number of people in our experiment, range from 10 to 100 in increments of 10, and we're going to look at this figure about how often is our ratio bigger than 4. And when I do that, okay, so it looks like at around 60 people we're a little less than 99%, but at 70 people we're getting to 99% certainty. As we get up to 100%, we're getting even more confident. And so it looks like I need about 70 people in my experiment before I would have any confidence that a result of 4 or better was not due to chance. So actually, it's not that many people, and it tells you why power analysis is so important. It suggests that this experiment might be worthwhile running. Okay? There's a footnote here where I expand on this idea, but I think I'll leave that to you for reading rather than further prolong this video. So this has been a discussion of statistical power, and it gives you an idea of factors that affect statistical power, such as the test in use and the number of samples being drawn.